Hello everyone. We'll be discussing about homework 2 in this video. Most of the problems are very straightforward. You have equations, you have to put values or parameter values inside the equation and you will get the result. Most of the problems are like that, but yeah, let's discuss however. The first problem was you have to calculate the energy of an electron in the third energy level of the potential oil. Okay, so the potential oil width was 3 angstrom. So there is a straightforward equation to calculate the energy at any energy level. So N is any energy level. So this is the formula where H cut square is equal to H divided by 2 pi. H is Planck's constant, you know that. N is the energy level number. In our case, it's 3 definitely. And pi square, which is a constant, 2m. M is the mass of the particle. The particle is electron here. So we have inserted the mass of the electron, which is 9.11 into 10 to the power minus 31 kg, and make sure that all the units are in SI, so that you will get the result is also in SI unit. Sorry about that. And yeah, and A is the width of the potential well, which is 3 angstrom, and angstrom you have to convert it to meter, of course. 1 angstrom equal to 10 to the minus 10 meter. So that's how you put all the parameters inside the equation, and you will get the result. So let's move to the problem number 2. Here you have to calculate the density of quantum states in per centimeter cube unit between these energy levels, which is EC and EC plus KT, where T is equal to 330 Kelvin. So some of you have confusion that why can't we use this formula directly? Why do we have to integrate this formula? I mean, integrate this equation. This is because this is density of states or quantum states in the per centimeter cube per electron volt or per unit energy density of states. But in the question of homework 2, you have to determine the density of states in all the energy levels between EC and EC plus KT. So not for a single energy level or per unit energy level, or per unit energy. So you have to integrate this from EC to EC plus KT. And for performing this integration operation, you can just take this constant because this whole term is a constant. So you can take this out from the integration and just integrate root over e minus ec. If you integrate root over e minus ec, you will get 2 divided by 3 e to the e minus ec to the power 3 divided by 2. Then you have to insert the parameter values in this equation or formula. You have got 4 pi, which is a constant, h cube. H is a constant, you know. And yeah, you have to put the upper limit and lower limit in the integration result as well. So you may ask, what is Mn star? You know that this is the effective mass of electron for density of states. In the question of homework 2, the value of this parameter is already given. Here, as you can see, density of states effective mass for electrons is 1.08. Here, the density of states effective mass is given in terms of m naught. I mean, this is 1.08 is equal to m star n divided by m naught, while m naught is the electron mass, or I mean, electron's mass is 9.11 into 10 to the minus 31. So the density of states effective mass of electrons would be 1.08 into m naught, right? So here what is given, mn star is equal to 1.08 into m naught. M naught is 9.11 into 10 to the minus 31 kg, right? And the other things are very straightforward. You have to just put the values like Boltzmann constant. You know that in SI unit it's 1.38 into 10 to the minus 23, and the temperature sorry, is given 330 K. So yeah, so if you insert if you want to calculate the integration result, where I told you that you have to put the upper limit and the lower limit. If you put upper limit and upper limit and lower limit in the place of E, you will get this. Okay. So yeah, then you will get the result because I have put all the values in the SI unit. So that's why the result also came in SI unit, which is per meter cube. But in the question, you are required to calculate this density of quantum states in centimeter cube. That's why you have to convert meter cube to, per meter cube to per centimeter cube. So yeah, let's move to problem number 3. Let's start problem 3. Here you have to determine the probability that an energy level 0.077 electron volt above the Fermi energy is occupied by an electron. So what is this value? The energy level is this much higher than the Fermi energy. So what is this? This is E minus EF. I mean the difference between the energy level and the Fermi energy level, which is 0.077. So we have a straightforward formula of calculating the probability, which is shown here. So E minus EF equal to 0.077 electron volt. To convert this to SI unit, definitely electron volt is not an SI unit for energy. So to convert this to SI unit, which is joule, you need to multiply this with E, right? So to simplify this, we actually transfer this E at the bottom of KT, which is exactly the same, right? That's how you can ease your calculation, or you can just keep the E here. And yeah, after plugging, after inserting these values, you'll get this result. So you will get 0.0626. To convert this to percentage, you have to just multiply it by 100.
So let's solve problem number 4. Here in this problem 4, assume that the Fermi level for a particular material is 5.33 electron volt. Okay, calculate the temperature at which there is 3% probability that a state 0.33 electron volt below the Fermi energy level will contain a hole. So let's at first understand the energy level. So, okay. So what is written here? That is set 0.33 electron volt below the Fermi energy level. So this is the EF, the Fermi energy level. And the energy level we're talking about is 0.33 electron volt below. Okay, so this is the electric energy level. So what can we write from this? We can write EF minus E is equal to 0.33 electron volt, right? Okay, let's go back to the question. So the question was at which temperature there will be a 3% probability of containing a hole. We do know the probability of containing an electron by Fermi reductive probability function here, as you can see. This is the probability of containing a hole, and containing an electron. So what will be the probability of containing a hole? So you know that electron's absence is hole. So uh, the probability of not containing an electron would be the probability of containing a hole. Okay, so what is the probability of not containing an electron? It's just the complementary 1 minus f of e here. F of e is the probability of containing an electron. So 1 minus f would be the probability of containing a hole. So just in this equation, just put the same fe here, and you will get the probability of containing a hole. And in this equation, you have to just plug in the numbers here, e minus ef. So maybe yeah, there is this little mistake here. So we have ef minus e equal to 0.33 electron volt. So e minus ef would be minus. This should be minus 0.33 electron volt. So there is a mistake in the solution. Just there will be a minus right here, and you have to calculate the equation, and you will get the result is correct actually. Although here is a mistake, but the ultimate result, the temperature value, is correct in the solution. So yeah, let's move to problem number 5. So let's start problem number 5. Here you have to calculate the thermal equilibrium hole concentration in silicon at T equal to 350 Kelvin. So they are asking you to calculate the P naught, the whole concentration at equilibrium. So P naught, they're asking you to calculate the P naught. And what is given here, assume the Fermi energy is 0.3 electron volt above the valence band energy. So what is written here, the Fermi energy, EF is 0.3 electron volt above. So this is the valence band, and the Fermi energy level is 0.3 electron volts above the conduction band energy level. Valence band energy level, right? So that's what is given here. So we can write EF minus EV is equal to 0.3 electron volt, right? Okay, and okay, so we have EF minus EV. So let's focus on what is required to calculate. So to calculate P naught, we have to write the equation. So let's focus on this equation first. So P naught. Let's see what we have and what we have to calculate. Which parameters already we have and which parameters we have to calculate. Let's determine it from this equation. So P naught is equal to this. So we do not know NV yet. Yes, there is NV given, but at a different temperature. So we don't have readily available NV right now to plug it into this equation. but we have these terms EF minus EV, which is already given here. It's 0.3 electron volt, and K is a constant, Boltzmann constant, and temperature is 350 Kelvin. And so we do not have NV yet. So to calculate NV, we have to use this proportionality equation, where there is the equation of NV actually, where if other terms are constant, then NV is proportional to T to the power 3 divided by 2. Using this, we can calculate the NV for a different temperature. For temperature 300 Kelvin, an NV is already given, so we have to calculate at a different temperature. So we can use this equation maybe. We can write NV at 350 Kelvin divided by NV at 300 Kelvin. This 350 and 300 are just subscripts here. And we can write 350, the temperature, and 300 as NV is proportional to T. The right hand side, these are T, are temperatures, to the power 3 divided by 2. We can write this from this proportionality. And from these, these are numbers we can easily calculate. And NV at 300 is already given, which is 1.04 into 10 to the power 19 per centimeter cube. From this, we can calculate the NV at 350, which we will require to plug in into this equation. So if you calculate NV 350, you will get this number, and just put it in, put this into this equation, and you will get the P naught value. Okay, so that's problem number 5. Let's move to the problem number 6. So let's start problem number 6. Here you have been given a germanium sample data. So focus on this. It's actually a germanium. Okay. So the doping concentrations are given, like Na and Nds are given. So you have to calculate the drift current density. I mean J drift. If the applied electric field E is 15 volt per centimeter. Okay. So let's straightly jump to the equation of J drift. I mean drift current density. This is the equation. So let's see what we have readily available and which are not readily available. We have to calculate. At first, it's E electron charge, simply electron charge 1 plus 6 into 10 to the minus 19. Then we have mu n. Okay. So what is the value of mu n? Remember, this is a germanium sample, and the mobility or mu n in the case of germanium, you will find this. You do not have to memorize this. You will find this in this table. Here in this table, as you can see, the mobility is given for germanium, which is electron mobility is 3900 and the whole mobility is 1900. So we have to use these numbers. And in the midterm as well, this table will be given. You do not have to memorize anything. So so we have mu n. Okay. So we have mu n, but we do not have the value of n yet. So we have to calculate this. And mu p, as I have already shown you in the table, the whole mobility is already given, which is 1900, and the whole concentration is not given yet. We have to calculate this P. So we have to calculate two things, N and P. So we have a readily available formula for N, I mean the electron concentration. Here's the formula, very simple. I mean, very simple to plug in. You have ND, I mean donor concentration, directly given 10 to the power 15 centimeter cube, per centimeter cube, sorry, and Na 10 to the power 14 per centimeter cube. So you have to plug it in all these things. And Ni, okay, so what is Ni for germanium? You can just go back to the table to find the Ni. So here's the value of Ni, intrinsic carrier concentration. Ni is basically intrinsic carrier concentration. We have to find this for germanium. The third column is for germanium, which is 2.4 into 10 to the power 13. However, in this solution, it's 2. We got 2 into 10 to the power 13 per centimeter cube, which is not exactly this value, but which is close. These values are not very much strict, but it's advised to use the value which is presented in the table. That's actually this comes from a different table. That's why this value is different. But you have to plug the value in which is written in the table. So use the table, okay. And you can calculate this in if you insert all the values, I mean all these concentrations in per centimeter cube, you will get the result in per centimeter cube. Okay. Then for the whole concentration, we have a formula. This formula comes from P n equal to Ni square. Okay, this is an important formula. So whole concentration into electron concentration equal to intrinsic carrier concentration square. So from this, we can calculate the whole concentration, because we already know the Ni, or intrinsic carrier concentration, and we already know the electron concentration. So you will get the value P. And again, the unit is not written here, but the unit is here, parts centimeter cube, because I have inserted the values in parts centimeter cube. So the result will also be in parts centimeter cube. Okay, so yeah, so we have P. So we have N, we have P, and we have all the required parameter values to plug it in into this equation, and you will get the current density value right here. And if in this equation you insert the concentration values in per centimeter cube, then you will get the answer in ampere per centimeter square. Okay, so keep in mind that if you insert centimeter per centimeter cube, you will get the answer in per centimeter square. I mean, this is the unit for current density. Okay, the ampere per area. So the area unit will be in centimeter square. Okay, so now let's move to problem number 7. Let's start problem number 7. It's pretty straightforward if you know the equation. So here the dielectric relaxation time constant, which we call as tau d, is given, which is 0.3 picosecond. Calculate the donor impurity concentration. Okay, donor impurity concentration. I mean, ND is required to calculate. So what is the equation here? We tau d. I mean, the relaxation time constant, dielectric relaxation time constant, tau d equal to epsilon divided by sigma, and we expand epsilon as epsilon r, epsilon naught. Epsilon r here is relative permittivity, or the other name of epsilon r is dielectric constant, and the epsilon naught is the permittivity in free space. Okay, I mean in vacuum, or maybe free space. Yeah. So we in this equation we know the value of tau d, which is 0.3 picosecond. We okay. So let's go to epsilon r. I mean, what is the value of epsilon r? I mean, relative permittivity or dielectric constant, that is given in the table actually. So epsilon r, I mean the dielectric constant. Yeah, here it is. So the dielectric constant is 11.7 for silicon. Now this problem is for silicon. So we will take this value 11.7, which is the value of epsilon r. And what is the permittivity in free space? This is also given in this level, which is epsilon naught, as you can see, 8.854 or 8.85 into 10 to the power minus 12 Faraday per meter. Okay, so yeah, epsilon naught is given already, and electron charge, it is electron charge simply, and mu n is the mobility of silicon, mobility of electron in silicon. So mobility of electron in silicon is 1350, 1350. Okay, and we do not know the ND, so we know all the values in this equation except ND, and from this we can calculate the value of ND. And look here, so epsilon r, we are putting epsilon r here as 11.7, right? Which is a dielectric constant, and epsilon naught, if you put the value of epsilon, look at the unit of epsilon naught. Okay, so if you use Faraday per centimeter, I'm keeping all these things in centimeter. Okay, so I am putting this value 8.85 into 10 to the minus 4 Faraday per centimeter. And in the case of mu n, uh, yeah, so mu n is centimeter square per ds. So all these things are in centimeter. I mean, instead of meter, we are using centimeter. If we use centimeter, okay, then the result would be in per centimeter cube. Okay, so let's move to problem number 8. Problem number 8 is very much similar to problem number 6. Right here, the donor concentration and sorry, and the acceptor concentration is given Na and Nd here, as you can see that Nd is greater than Na, so you can use this formula to calculate it. So let's come back here later. So what is required? We have to calculate the current density, drift current density. Okay, so this is the formula of the drift current density, and we know the value of E, which is 1.6 into 10 to the power minus 19, and mu n, I mean the mobility of electron in gallium arsenide, because yeah, this problem is for gallium arsenide. So jump to the table. Here is the gallium arsenide. Find the mobility. Here is the electromobility and hole mobility for gallium arsenide. So electromobility is 8,500 and hole mobility is 400. So we already know the mu n and mu p from the table. So we got mu n and we got mu p, and we do not know n and p. Okay, I mean the electron concentration and the hole concentration, and we know E. Already, this is already given. E is 15 volt per centimeter. Again, in this equation, I will be keeping all the units in centimeter, like thing. I mean, not meter, we'll be using centimeters. So we have to calculate N and P as ND. I mean, the donor concentration is greater than the acceptor concentration. We can use this formula ND minus NA divided by 2 and blah, blah, blah. We know ND and NA, right? We do not know NI yet. We have to go to the table to get the value of the NI, I mean, the intrinsic carrier concentration. So let's go to the table and find the intrinsic carrier concentration for gallium arsenide. Let's find that intrinsic carrier concentration. Here it is. So for gallium arsenide, it's 1.8 into 10 to the power 6. We have to just plug it in this equation and you will get the value. And so here you will get the value of N, I mean electron concentration. And again, from this formula, Pn equal to Ni square, you will get, you already know the value of N, you already know the value of Ni square, and from this you will calculate the electron concentration, sorry, hole concentration, which is P. And after that, we will have all the parameters inside this equation. So we will just insert the values and we'll get the drift current density for this problem. Okay, let's move to problem number 9. Number 9, I'm not even going to talk about this because it's exactly the problem of, the problem of problem number 1. The values are different only. So I'm just skipping it, going to problem number 10 directly. So determine the probability that an energy level 0.05 electron volt above the Fermi energy is occupied by an electron. This was also a similar problem that was discussed in the earlier earlier problems. So let's discuss this. Okay, so this is even easier than the previous problem actually. So this is you have to calculate the probability of containing an electron. So we have a Fermi Dirac function and the energy level, as you can see, an energy level 0.05 above the Fermi energy. So if this is the Fermi energy level, the energy level we are talking about is 0.05 above the EF. So we can write E minus EF is equal to 0.05 electron volts. Okay, so just put this into this equation, and the temperature is also given. You know the Boltzmann constant, and so as this is in electron volt, you can write this in. You have to write this in joule actually. So to write this into joule, I mean in the SI unit, you have to multiply this with the electron charge, which is E. So okay, so 0.05 into E, I mean the electron charge, which is actually sent at the denominator right here. Okay, so this was actually in here. It's so it's put back. I mean, it's sent into the denominator of this KT. Okay, whatever. You will get the value or probability. So let's move to problem number 11. This is same problem like homework 1. The de Broglie wavelength, I mean lambda is given 50 angstrom. Determine the electron energy, momentum, and velocity, etc., etc. So from lambda, you can actually calculate everything because according to the de Broglie formula, we can write this P equal to h divided by lambda. P here is the momentum. H is a constant, I mean Planck's constant. Write everything in SI unit, and then you will get the momentum. So from momentum, we know that momentum formula is P equal to mv, and V, I mean the velocity is equal. You can calculate the velocity V from here. P, you already know P, you know M because this is electron. So we know the mass of electron, which is 9.11 into 10 to the minus 31. And from there, you will get the V, and we have the energy formula E equal to half of mv square. You know M, you know V. Just put them into the equation, you will get the energy. Okay, as you have put all things in SI unit, you will get the energy in joule unit. If you want to convert this to electron volt unit, just divide this with electrons charge and you'll get the result in electron volt unit. So now let's move to the problem number 12. So problem number 12, this is exactly the same problem of homework 1, problem number 4b. So you can go and check. There is a solution video and solution PDF for homework 1. You can go there, and this is exactly the same problem of problem 4b of homework 1. So number 13, so you have to, some topic concentrations, temperatures are given. So you have to calculate the built-in potential, I mean potential barrier, which is called PBI, and the space charge width at zero bias. So space charge width is W. So we have to calculate PBI and W at zero bias. Here we got the formula for PBI. So everything is actually given straightforward. K is the Boltzmann constant, T is the temperature, which is 300 Kelvin, E is the electron charge, Na and D is also given. And yeah, Na and Nd are given in per centimeter cube. So you have to put that in per centimeter cube. And as the denominator will also be in per centimeter cube. So yeah, so Ni, I mean the intrinsic carrier concentration for this is silicon. So the Ni value is 1.5 into 10 to the power 10. And you will find this value in the table. Let me show you that. I mean intrinsic carrier concentration. This is the intrinsic carrier concentration per centimeter cube for silicon, which is 1.5 into 10 to the power 10, which is inserted here. And you will easily get the value of VBI, 0.695 here, 0.695 volt. And let's move to the space charge width. So we have 2ES divided by 2ES VBI divided by E. So in the width formula, so what is epsilon S? It's basically epsilon R into epsilon naught. Epsilon R is the relative permittivity or dielectric constant, which is given in the table. Yeah, dielectric constant for silicon is 11.7. Okay, so the epsilon value of epsilon R is 11.7, and epsilon naught, I mean permittivity in free space, which is given in this table, 8.854 into 10 to the power minus 14 farad per centimeter. And the electron charge, Na and D, just insert them into the equation, and do not forget this power half. Okay, so typically people forget to include this half or calculate this half. I mean, then you will get the result in centimeter. If you wish to convert it to any other unit like micrometer, you can just convert it, or you can keep it like this. So this is problem number 13. Let's move to problem number 14. Here you have to sketch the band diagram of a silicon-based p-n junction at thermal equilibrium. Okay. So let's draw this. Suppose suppose this is p side and this is n side, and this is the conduction band, and this is the valence band. Okay. So in P, the Fermi level should be near or closer to the valence band, right? This is the Fermi level. So how about the n side? Okay, so for the n side, just that after connecting the p and n junction, the Fermi level should be straight. Okay, so for the n side, as you know that in the n side, the conduction band should be closer to the Fermi level rather than the valence band. So I suppose this is the conduction band. This is the conduction band, and this is the valence band. Because in the n region, EF should be closer to EC. What will be in the junction? So EC, this is the EC, and this is the EC for this EC is for the P side, and this EC is for the N side. So in the junction, there will be a bending, right? Okay, and for the EV as well, there will be a bending to match the EC, because EC will not be abrupt here. DC will change smoothly, so that's why I have shown a smooth change in the junction, and this is applicable for the valence band as well. So yeah, so you have to check that in the P region, is the AF close to EV? You have to make sure that, okay, so EF should be nearer to EV in the P area, I mean in the P side, and in the N side, EF should be close to EC. That is the p-n junction band diagram at thermal equilibrium. So yeah, that's it. Thank you for listening.